All right, friends, this should be lots better quality than yesterday. Apologize again. All right, pausing my talk 'cause I'm trying to see if my cat's going to chew on the cord. No, he's just looking at it. All right, waves. Something's weird about this in that I can't quite get far back enough. So it's waves, okay? Waves. That's today's lesson, waves. That's all the notes on the page. So take that down. All right. Transverse waves have particles that move perpendicular to the direction of the flow of energy. So think a guitar or a boat. I like the idea of a guitar string. I think you strum down on a string. If the strings are the same kind of orientation as these words, you strum down, the waves go away. Okay, that's a transverse wave. Longitudinal wave is particles that move parallel to the direction of flow. Whenever you think parallel, I often think next to. It doesn't mean next to as much as it means in the same direction. Okay, so push on a slinky. If I push on a slinky, it's like in the same direction. It makes that sound. Just listen. In fluids, when longitudinal waves travel through regions of higher pressure, those regions are called compressions. Rarefactions are regions of lower pressure. Rarefactions is probably a rarefied word and you haven't heard it too much. Pair it with this, because you know what compressions means. You know what it means to compress. Yes, compress. So compressions, rarefactions. Try and remember those two. I just said member. Sound is a longitudinal wave produced by rapidly vibrating objects. Longitudinal is one that pushes, right? When you think it comes from the source. Most wave motions in nature are a combination of longitudinal and transverse motions. Very little of what we do and what we've done so far in physics is real world. It's all baby steps. We talk about crawling as if this is high speed wave motion dispersing energy. We're going to start talking about how to walk yet. Do you know what I mean? You know what I'm saying? Is it the dumbest example I've given? We have a ways to go. Everything's complicated. Everything that we've been doing so far, it's like assume there's no air resistance and it's no friction. Well, it's just not real. But we need to do that first before we can do the heavier stuff. Cool. All right. Can I get all of this on the screen from wavelength? Yeah, I think so. This shadow bugs me, but I guess that's what it is. I'm in a new place for my desk, for my workspace, and I'm not sure how to get rid of that. If we go up a bit. No, that was not nearly as hard as I thought it would be. Has to do with also I got a window above me, so that natural light changes throughout the day. See, that was a bird that just flew by. All right, I'm assuming you've copied this all down. Good. Wavelength, that's lambda. If you want to write it down so you don't forget. I don't know how to spell it. I'm just spelling it phonetically. You don't need to spell it. Just remember how to say it. Lambda. Matthew TD would always call it sheepda. Wavelength is the distance or length of a wave cycle from crest to crest or trough to trough. Our handy little figure here. You should have covered this stuff in grade 8. That doesn't mean, I kind of hate it when teachers say that. Doesn't mean you remember every single thing you've ever done. But I'm saying it in the sense that you should remember hopefully it's familiar, as I guess what I'm saying. Wavelength, from crest to crest. It can be from trough to trough. It can be, like see how this is the downside at the equilibrium point. It could be from here to here. Okay, this is the easiest, crest to crest. It's basically it's one full movement of the wave, one full repetition, one full cycle. That's what I'm looking for. Amplitude is the maximum distance of a vibrating particle from the equilibrium point. It's like top to middle. Okay, it's not top to bottom, top to middle. This is amplitude, which also means this is amplitude. Okay, I've got something on my screen, but it's from the camera. I'm assuming you can see this. Tell me if you can't. Phase shift is the amount that one waveform is displaced along the x-axis. So see, from this bad boy, if this whole thing was moved over to here, okay, that's a phase shift. A waveform is a kind of drawing of a wave. That's a waveform. These are good words to know. Test would almost always have like draw a waveform and label it, and then draw a waveform with a phase shift, something like that. So you want to make a little note of that. Oh, I'm going to add that to my test. Be a good idea. That's what good tests have. It's all on the screen. It is, just barely. Oh, you got it copied? Oh, amazing. Period. Capital T. Period. Period and frequency, you have to kind of screw it into your brain to make sure you get it down. It's a subtle, inversely proportional difference. Period is the time it takes for a vibrating particle to complete one cycle. So if we talk about the wave, it goes like this. That time is the period. Because it's time, period is in seconds. Okay? Period, capital T, time, period, in seconds. Frequency is the number of cycles of a wave that occur per second. So for one wave, let's say it's 0.0084 seconds or something like that. But how many of those happen in 1 second? Oops, that's your frequency. Number of cycles, so it's going to be cycles per second or hertz. I think I've got the, why are the units not down here? I'm going to pause this. All right, welcome back. I have no idea why I didn't put the units here. Period is seconds. Frequency is cycles per second or hertz. Okay, just so you know, frequency is in hertz. You can cycles per second if you want, but I wouldn't. Or hertz. Time is in, period is in seconds. Capital T, think of time. Period is in seconds. These two bad boys are inversely proportional. If you have one, you can find the other. F, frequency, is 1 over time, 1 over period, 1 over seconds. And period is 1 over hertz, 1 over cycles per second. Okay? Cool. Wave speed is the rate that a wave moves through a medium, which is in V. Notice there's no arrow over top. That's intentional this time. It's talking about speed, it's not velocity. You can find it through, wavelength over period. Wavelength's in meters, period is in seconds, so meters per second. Length of one cycle, or over the time for one cycle. Okay, that's how you get the wave speed. That's how you know how fast it is. Simple harmonic motion is any type of oscillation or vibration that repeats itself at irregular intervals about an equilibrium point. We talked about the like a pendulum. That's a chain, clearly, that I'm drawing, because what I have in my head right now is like a punching bag. That's pretty good. Can you even see all of it? Cat hair everywhere. Look at that's a good punching bag. So if like Karina punched it, it wouldn't move, right? Because she's not very strong. But if anybody else hammered this thing, then it would sway, and then you leave it and it comes back to its resting point. That would be simple harmonic motion. That's assuming the chains don't, clink up and tighten up and get caught in each other, blah, blah, blah. Okay, is everybody else getting tired of hearing my voice? Now here's the catch. This is 2 lessons in 1. Two lessons in 1. It looks like, just a quick glance, like, what the heck, why 2? It's 8 questions. There aren't even any practice questions. There aren't even any tutorial questions for this. So, it's pretty straightforward, my friends. Have a lovely Friday, lovely weekend. That's all I got. See ya.